All right, let's talk about something that's super important for electrical safety, but it's often totally overlooked. I'm talking about bus bar sizing. Now, I know that sounds really technical, but trust me, getting this wrong, well, it's a huge fire risk hiding right inside the walls of pretty much every large building. So we're going to break down how it works and, more importantly, why it matters so much.
So, let me ask you this. What do you think is a leading cause of fires in big electrical switchgear? Those massive panels that run our buildings. You might guess it's some kind of complex computer failure or maybe a really high-tech problem. But the real answer? It's actually way, way simpler than that.
Yep, it's an undersized metal bar. That's it. Just a simple piece of copper or aluminum that wasn't made big enough for the job it was supposed to do. And that little component, well, that's called a bus bar.
So what exactly is a bus bar? Well, the easiest way to think about it is like the main highway for electricity inside a big electrical panel. It's just a solid metal bar that's built to handle enormous amounts of current and, direct all that power to where it needs to go. It's a simple idea, really, but it's absolutely critical. Okay, now here's where we get to the core of the problem, and it's some basic physics that you just can't get around. Anytime, and I mean anytime, you run electricity through a conductor, it creates heat. It's called joule heating, and the more current you jam through it, the hotter it gets. This right here, this is the heart of the whole issue.
And this quote really nails it. This is probably the most important thing to understand. Sizing a bus bar isn't just a simple Ohm's law calculation. Nope, it's a thermal management problem. The real question engineers have to solve is, how do we get rid of all that heat before something terrible happens? Before it fails completely.
All right, so this brings us to the very first big choice an engineer has to make, and it's a decision that affects everything else down the line. What material are you going to use? And really, it boils down to a classic showdown: copper versus aluminum.
And right here, you can see the fundamental trade-off. Look, copper is hands down the better electrical conductor, no question. But then you look at the other numbers. Aluminum is way, way lighter, and it's a lot cheaper. So you've got this classic engineering problem, right? Do you go for pure performance, or do you prioritize saving on cost and weight?
And that big difference in conductivity you see here, it has a huge impact in the real world. Because copper is so much better at conducting electricity, you can use a much smaller bar to carry the exact same amount of current. Now think about a crowded electrical panel, where every single millimeter of space counts. That's a massive, massive advantage.
Okay, so we know these things are going to get hot. The big question is, how hot is too hot? I mean, where's the line? Luckily, we don't have to guess. There's a major international standard that gives us a hard limit. It's basically the golden rule for every single designer. And that number is 70. The big international standard, it's called IEC 614390-1, it says the absolute maximum temperature rise you can have is 70 Kelvin. Now, since we're talking about a change in temperature, 70 Kelvin is exactly the same as 70 degrees Celsius. This is it. This is the safety ceiling. You can't go past it.
And it's really important to get what temperature rise actually means. We're not talking about the final temperature of the bus bar itself. No, we're talking about how much hotter it gets compared to the air around it. And why do they do that? Well, it means the standard works no matter where you are, whether you're in a freezing cold data center in Iceland or a sweltering hot factory in the middle of a desert. Okay, so we've got the problem, which is heat, and we've got our safety limit. So how do engineers actually put this all together and design a system that's safe? Well, they don't wing it. They follow a really rigorous 7-step process.
And you can see this is not guesswork at all. You start by figuring out the current you need to handle, you pick your material, you figure out the target current density, and then you can calculate a minimum size. But then, and this is the most important part, you have to verify everything. You check that temperature rise, you apply factors for real-world conditions, and you even make sure it can handle a worst-case scenario like a short circuit. It's a step-by-step path to making sure things are safe.
You know what? To make this feel a little more real, let's actually walk through an example. We're going to look at a super common scenario: sizing the main copper bus bars for a 2,000 amp distribution board. This is the kind of heavy-duty gear you'd find powering a big commercial building. So at the heart of all this is a pretty simple formula. You just take your total current, in our case 2,000 amps, and you divide it by something called current density. Now, a good way to think of current density is like a safe speed limit for the electricity flowing through your material. And for copper, a pretty standard value to use is 1.4 amps for every square millimeter of area. You run those numbers and the math spits out a minimum required area of about 1,429 square millimeters. Now this is our starting point. It's the absolute smallest that bar can possibly be, assuming, we live in a perfect world.
But, of course, the real world is not perfect. Electrical rooms get hot. And to account for that, engineers have to apply what's called a derating factor. Think of it as a safety buffer. It's an adjustment that basically says, hey, it's hotter in here, so it's going to be harder for this bus bar to cool off, so we need to be more conservative. And you can see just how much of a difference this makes. The standard is based on a starting room temperature of 35 degrees Celsius. But what if the room is actually 40 degrees? Well, suddenly that bus bar can only handle 91% of what it's rated for. And if it gets up to 50 degrees, you're down to just 71% of its capacity. You can see how ignoring this, well, it's just a recipe for disaster.
So, let's bring all this home. We've talked about the physics, we've looked at the materials, the safety standards, and the whole design process. So, what's the big takeaway here? What's the bottom line?
Really, it all boils down to three things you just can't compromise on. First, the physical size of the bus bar. Its area has to be right for the current it's carrying. Second, you absolutely have to check the heat it produces against that international safety limit, and you have to correct it for the actual temperature on site. And third, that very first choice you make, copper or aluminum, that sets the course for the entire rest of the design. You get these three things right, and you've built a safe system.
This whole thing is such a perfect example of the kind of invisible engineering that keeps our world running. It's happening all around us, all the time. And it kind of makes you wonder, right? What other critical engineering choices like this are hiding just out of sight, silently keeping our lights on and our world powered safely every single day?